What if you could see through the ground without ever digging a single hole? Seriously, what if you could map out hidden chambers, old tunnels, or natural voids just by using the power of cosmic rays and maybe a little help from nature itself? Well, today we're going to dive into a really fascinating theoretical concept for a brand new kind of detector, one that fuses cutting-edge physics with some of biology's oldest and smartest tricks. All right, so here's our game plan. First, we'll set the stage and talk about the challenge of seeing underground. Then we'll get into the two super senses this whole idea is built on. After that, we'll look at how you'd actually build the thing, explore the absolutely brilliant bio-inspired upgrades, and finally, we'll see what success would really look like in the real world. You know, for people like archaeologists, geologists, and even engineers, one of the biggest headaches is just figuring out what's right under our feet. Trying to find a hidden tomb or a cavern filled with water, or even just an old utility pipe. It's usually a slow, really expensive, and sometimes destructive process.
And that leads us to the big question that drives this entire concept. How do we find a better, non-invasive way to see all that hidden stuff? How do we build a tool that can effectively peer right through solid ground? Well, the answer, it turns out, might not come from just one technology, but from a really clever combination of two.
Okay, this is where we get to the heart of the protocol. See, instead of trying to reinvent the wheel, this concept starts by taking two existing and very powerful sensing methods and just smashing them together into something way, way more powerful than either one alone. So let's break down these two senses, because this is really cool. On one side, you have muography. Think of it like nature's own X-ray machine. Cosmic rays are hitting Earth all the time, and they create these tiny particles called muons. Now, muons pass through pretty much everything, but they get slowed down or even stopped by really dense stuff. So by counting how many get through, you can spot areas that are less dense, like a hidden chamber or a void. Then on the other side, you've got magnetometry. And we're not talking about your pocket compass here. We're talking about super sensitive instruments that can measure tiny little wiggles in the Earth's magnetic field. This makes them awesome for finding things like metal objects or even geological changes that are linked to underground water. And that all brings us to the official name, the Mu-Al-B protocol. Yeah, it looks a little complex, but it's actually super elegant. The mu, that's the Greek letter mu, stands for muons. The VB represents the gradient or the change in the magnetic field. And that circle with the plus sign in the middle, that's the symbol for fusion. It's all about bringing these two different senses together into one unified system. And this right here, this is the big idea, straight from the source. The hypothesis is that by combining the density map you get from muons with the material map you get from magnetometry, you end up with a much, much clearer and more reliable picture of what's underground. You don't just see that something is down there, you start to get a much better idea of what that something might be. So, how would you actually build one of these things? Let's get into the nitty-gritty of the design and see how all these pieces are supposed to come together, from the sensors themselves all the way to its protective shell. So conceptually, it all starts with the core sensors. You've got these two special scintillator paddles, which are basically materials that give off a tiny flash of light whenever a muon zips through, and they sit right alongside a super sensitive magnetometer. All of that gets packed into a single, tough, weatherproof box. But here's the really slick part, the noise boundary. It's this special honeycomb structure that basically acts like a pair of noise-canceling headphones for the whole device, filtering out all the vibrations and sounds that can mess up the very delicate measurements. And the performance goals for this device, well, they're incredibly ambitious. I mean, just look at this. It's aiming to pinpoint a 1 cubic meter void with an accuracy of less than a meter. And get this, it's designed to run on less than 5 watts of power. That's almost nothing. It means you could just leave it out in some remote location for a super long time. It's this amazing combination of extreme precision and incredible efficiency. Okay, so if fusing two fields of physics wasn't cool enough for you, this is where the concept really just launches into the realm of science fiction. It does this by borrowing engineering solutions directly from nature. And these aren't just little add-ons. They're designed to be integral, performance-enhancing layers. And this is where it just gets wild. The concept lays out these optional nature-inspired upgrades. I mean, imagine surrounding the detector with a mat made of pollen to act as a natural sound and dust filter. Or, get this, integrating a tiny compass that uses magnetic biomaterial to orient itself. The whole idea is to create a symbiotic design, where the detector actually works with its environment to get cleaner data. But this might be the most incredible idea of the whole bunch, a living acoustic damper. The concept suggests using a thin layer of living moss that can actively change its own moisture levels. Why? Well, by doing that, it can literally tune its own acoustic properties on the fly, adapting in real time to dampen whatever specific sound frequencies are causing interference at that exact moment. It's an active, adaptive, living component of a physics detector. It's just wow. So, this all sounds absolutely incredible, right? But I know what you're thinking. How do you take such a futuristic idea and actually prove that it works? Well, the concept paper lays out a very clear, very practical path to get from a theory on paper to a real-world field test. It's a classic step-by-step scientific progression. First, you test the core components on a lab bench to make sure everything works. Then you build a small array, maybe 3 detectors, and see if you can find known objects, like a pipe or an empty space behind a wall. And finally, if all that works, you move to a pilot study, deploying a whole network of 10 to 30 of these nodes out in the field to create a complete 3D map of whatever's underground. So what's the ultimate prize here? What's the end game? It's this number. The goal is to achieve sub-meter resolution, to get the accuracy down to less than half a meter. With a scaled-up array of these detectors, you could map the underground world with a level of detail that is just completely impossible right now without digging everything up. It would be a true game-changer for exploration and discovery. So we're left with this final thought. The mu+v protocol is, for now, still a concept, a brilliant what-if on paper, but it really pushes us to ask a much bigger question. As we search for new ways to explore our world, will the greatest breakthroughs come not just from mastering physics, but from learning how to partner with biology? Maybe, just maybe, to truly see the unseen, we need to fuse them both together.